space itself may be pushing everything apart faster over time. Current observations suggest that the farther galaxies are from us, the faster they appear to accelerate away, even though gravity should slow large-scale expansion down across cosmic time. The anomaly did not emerge from a single object or isolated region. It appeared across the observable universe through redshift measurements, where distant galaxies showed expansion patterns stronger than earlier cosmological models predicted. The observable pattern was not merely expansion, but accelerating expansion. For much of modern cosmology, expansion was expected to behave differently. After the initial outward momentum of the early universe, gravitational attraction between galaxies and matter structures should have gradually reduced the expansion rate. Current observations suggest the opposite trend may be occurring. The contradiction becomes more severe at larger distances. Nearby galaxies follow one expansion behavior, but extremely distant systems appear tied to a universe that expanded more slowly in the past than it does now. The acceleration seems to increase across cosmic scale rather than weaken. The observable signal responsible for this conclusion is not direct motion through space. The evidence comes from redshift acceleration gradients, where light from distant galaxies stretches in ways that imply increasing separation over time. The mechanism producing that increase remains physically unclear. The known system still explains many large-scale structures successfully. Gravity governs galaxy formation, cluster interactions, and orbital behavior with extraordinary precision. The problem emerges when those same gravitational expectations are extended to universal expansion itself. The universe appears to behave as though an additional component exists within space. Current models describe this through a dark energy field, but the label explains the observation more than the mechanism. The accelerating behavior is measurable, while the physical origin remains unresolved. This creates the first major mechanism boundary. Expansion itself is not unusual within cosmology, but self-accelerating expansion introduces a force-like effect that does not fit cleanly into known large-scale gravitational behavior. Space may contain an energy component that counteracts gravitational slowing. The contradiction sharpens when scale is considered directly. Inside galaxies, gravity pulls matter together into dense structures. Across universal distances, the dominant trend appears reversed, where separation increases faster over time instead of stabilizing or slowing. A familiar physical expectation begins to fail under extreme scale. Gravity weakens with distance, but current observations imply that something increasingly dominates as scale expands outward. The larger the cosmic framework becomes, the less gravity appears able to control its long-term behavior. This creates a mechanism imbalance rather than a missing observation alone. The expansion field is not behaving like ordinary matter, radiation, or known energy transfer systems. Current models can mathematically describe the acceleration while still lacking a physically verified cause. The acceleration also produces a measurement problem tied directly to cosmic history. Observations are always delayed by the travel time of light, meaning astronomers reconstruct expansion by comparing different eras of the universe simultaneously. The observable pattern emerges only after combining enormous distance scales across time. The deeper the measurements extend, the stranger the implication becomes. Earlier epochs appear more gravitationally dominated, while later epochs suggest a growing expansion effect embedded into space itself. Something may have altered the balance of the universe without any directly observed transition point. One possible expectation was that dark energy might weaken over time. Current observations have not confirmed that behavior. Another expectation was that acceleration could stabilize into equilibrium, but available measurements still leave that outcome uncertain. The known expansion system therefore reaches an incomplete boundary. Cosmology can model how the acceleration behaves mathematically across universal scale, yet the mechanism responsible for injecting that behavior into space remains unidentified. The effect is observable while the source is hidden. The anomaly also reframes the meaning of empty space. Vacuum regions were once treated largely as passive distance between structures. Current expansion behavior suggests empty space itself may actively influence cosmic evolution, which fundamentally alters the expected role of the vacuum in large-scale physics. This creates another contrast between observation and mechanism. The universe behaves as though space possesses an intrinsic outward pressure, yet no directly observed physical structure has been isolated as the driver of that pressure. The observable consequence is clearer than the mechanism producing it. The scale of the acceleration further weakens intuitive interpretation. Individual galaxies do not visibly explode outward, and local gravitational systems remain stable. The effect only dominates across enormous cosmic distances where expansion accumulates gradually over billions of years. The observable universe therefore separates into competing physical behaviors. Local structure formation still depends on gravitational attraction, while universal-scale expansion increasingly reflects outward acceleration. Both systems appear to coexist simultaneously without a fully unified mechanism. The deeper problem is not simply that something unknown exists. The problem is that the unknown mechanism increasingly dominates the long-term evolution of the universe itself. A secondary effect appears to govern the largest physical scales while remaining physically unidentified. Current models can estimate the proportion of the universe associated with dark energy-like behavior, but estimation is not equivalent to understanding. The measurements describe the acceleration pattern successfully while still leaving the physical nature of the expansion field unresolved. The acceleration gradient ultimately pushes cosmology into a mechanism breakdown rather than a completed explanation. The universe behaves consistently enough to measure, yet the force-like behavior driving that consistency remains hidden behind observational effects instead of directly observable physics. The further observations extend across scale and time, the more stable the acceleration pattern appears to become. That consistency strengthens the anomaly instead of resolving it, because the universe continues behaving as though space itself contains a dominant physical property that current models still cannot fully explain. The acceleration does not remain isolated to distant galaxies alone. Over sufficiently large timescales, increasing expansion alters the relationship between every large-scale structure not held together by strong local gravity. Separation compounds gradually across billions of years until distance itself becomes dynamically dominant. This creates a propagation effect embedded directly into cosmic geometry. Expansion is not moving galaxies through space like debris through an explosion. The structure of space between them may itself be changing, which makes the mechanism harder to isolate physically. The observable pattern therefore carries an unusual dependency. Every measurement of acceleration relies on light that has already crossed expanding regions of space, meaning the signal itself may be altered by the same phenomenon being measured. Observation and mechanism become partially entangled. Current models can still trace expansion backward toward earlier cosmic states. The difficulty emerges when projecting the same behavior forward indefinitely. A mechanism that continuously amplifies separation eventually reshapes the long-term structure of the observable universe itself. The contradiction becomes sharper when structure formation is examined at extreme scale. Gravity successfully assembled galaxies, clusters, and large-scale cosmic networks over billions of years. Yet the same universe now appears increasingly governed by outward acceleration rather than large-scale accumulation. This implies that the balance between attraction and expansion may not be fixed. A small dominance shift at universal scale eventually propagates into enormous structural consequences because expansion compounds continuously across distance and time. The acceleration also introduces a boundary condition problem. If dark energy remains stable or strengthens, distant regions of the universe may eventually recede beyond observable interaction entirely. Observable structure would not collapse physically, but become permanently disconnected through expanding space. The anomaly therefore escalates from a measurement issue into a causal isolation problem. The universe may evolve toward increasing observational separation, while the mechanism driving that separation remains unidentified. Another limitation appears inside the redshift measurements themselves. Expansion rates are inferred statistically across vast populations of distant objects rather than observed directly in real time. The acceleration pattern emerges only after reconstructing cosmic history through layered observational inference. This creates analytical tension inside the model. The expansion trend appears remarkably consistent across independent observations, yet the physical cause still behaves more like a fitted requirement than a directly observed mechanism. The data stabilizes the anomaly without clarifying its origin. The scale amplification becomes more severe over longer temporal projections. Small increases in expansion rate produce relatively subtle early effects, but compound dramatically over universal timescales. A weak, large-scale force can eventually dominate the fate of cosmic structure entirely. The known equations continue functioning mathematically across these projections. The breakdown occurs conceptually because the equations describe acceleration successfully, while remaining unable to explain why empty space behaves this way physically. This distinction matters because predictive accuracy is not equivalent to mechanism understanding. Cosmology may estimate how expansion evolves without identifying what property of space generates the effect. The observable universe behaves consistently while the underlying cause remains hidden. The anomaly grows stronger when compared against ordinary energy behavior. Most known physical systems dilute as space expands, with density decreasing over larger volume. Dark energy-like behavior appears different because the acceleration effect does not weaken in the same expected way. That mismatch creates a deeper mechanism instability. If the expansion field remains uniformly embedded into space itself, increasing spatial volume may not reduce its large-scale influence. Expansion would then amplify the conditions supporting further expansion. The propagation effect becomes self-reinforcing at universal scale. More expansion creates more space, and more space may preserve or amplify the same acceleration behavior already observed. Current models can represent this mathematically while still lacking direct physical explanation. This pushes the anomaly beyond ordinary missing data problems. The issue is no longer simply that some variable has not been measured yet. The observable behavior itself may emerge from properties of space that cannot currently be isolated experimentally. The measurement boundary tightens further because no local laboratory reproduces universal-scale expansion conditions. The acceleration effect only becomes dominant across immense distances and timescales, making direct physical verification extraordinarily difficult. The universe therefore presents a mechanism visible only through cumulative consequence. Individual galaxies do not reveal the anomaly clearly in isolation. The contradiction emerges only when expansion is traced across enormous cosmic intervals where tiny deviations accumulate into measurable acceleration. That accumulation introduces another unresolved dependency. If the effect changes even slightly over time, projections of the universe's long-term evolution shift dramatically. A nearly imperceptible variation in expansion behavior could alter the structure of the future cosmos at the largest possible scale. The observable pattern nevertheless continues pointing in the same direction. Expansion appears not merely persistent, but increasingly dominant across universal structure. The larger the scale examined, the harder it becomes to explain why gravity no longer controls the system cleanly. The acceleration field therefore remains physically incomplete in a critical way. Cosmology can observe the consequences spreading through space and time, but the mechanism responsible still exists primarily as an inferred requirement imposed by the behavior of the universe itself. The universe is no longer understood as a system expanding outward from an ancient event alone. Current observations suggest the expansion itself may now be controlled by a deeper property embedded into space, one that increasingly dominates the largest observable scales while remaining physically unidentified. What changed is not the detection of motion, but the interpretation of empty space. Regions once treated as passive distance now appear connected to a mechanism capable of overcoming gravitational slowing across the entire observable universe. Yet no confirmed physical structure fully explains why that happens. The equations describing acceleration continue functioning with remarkable precision. The boundary appears when those equations are forced to answer what the expansion field actually is, because the observable behavior remains measurable while the underlying mechanism still cannot be directly isolated. That leaves cosmology in an unstable interpretive position. The universe behaves as though space itself contains a persistent outward driving component, but the farther observations extend across scale and time, the more the effect resembles a dominant physical reality without a confirmed physical cause. The anomaly, therefore, does not close into a solved mechanism. The observable universe continues accelerating exactly where gravity was once expected to regain control, and current models can describe the expansion with increasing accuracy while still stopping short of explaining why space behaves this way at all.